Hello, I am Keke. Today we start a new series of physics lessons on gravity and mechanical energy. Join me as we focus on a very particular kind of motion, falling. In this lesson, we are going to answer questions about how and why things fall. We rely on the fact that all things fall down. If things sometimes fell sideways or backwards, or if things fell upwards, we wouldn't, for example, be able to use heavy machinery to move sand and rock from one place to another. Watch as this young diver trains on a diving board. He too knows that what goes up must come down. And of course you know this too, but have you ever wondered why? How does this juggler catch each ball at exactly the right moment? How does he manage to do this with objects that all have different sizes and masses? Questions about why things fall down and how they fall have interested people throughout the ages. The Greek philosopher Aristotle, the Italian physicist Galileo, and the English physicist Newton all tried to answer these questions. In this lesson, we'll try to find some answers together. By the end of this lesson, you should be able to identify and explain what affects the motion of falling objects. Design and conduct an experiment to investigate how an object falls. Interpret data gathered from an experiment. Explain why objects fall. To start with, let's find out what Aristotle had to say about falling objects. I believe that any thinking person can see that heavier objects must fall faster than lighter objects. Just think about it and you will agree with me. Do you think Aristotle was correct? Well, at the time most people did. You see, Aristotle was a much respected philosopher. But in the 16th century, Galileo Galilei thought that Aristotle might actually have been wrong. So he decided to design an experiment to test his theories. Galileo lived near a town called Pisa in Italy. This town has a very famous tower. It is famous because it's leaning to one side. Actually, it's slowly falling over. Legend has it that Galileo dropped balls of different mass from the top of the Tower of Pisa to see if there were differences in how fast they fell. Do you think you could design an experiment similar to Galileo's? Well, I'm going to take 2 learners to the lab to see if Aaron can help us set up an experiment of our own. As you watch our progress, take note of how we ensure that our test is fair.
Hey guys.
Hi, Aaron. What are you doing up there?
Well, you guys wanted to set up an experiment similar to Galileo, didn't you?
That's right.
Come up the stairs. I'll show you the apparatus I've put together. See, I took 3 balls, all different colors and all different masses. So now we're going to throw them down at the same time.
You see, the purpose of this experiment is to see whether the mass of an object affects how fast it falls.
So, if you release the balls at exactly the same time and then measure the time it takes for the balls to reach the floor, that should answer a question.
That sounds right, but that means we'll need some more equipment.
Right. We will need a stopwatch and something that will release the balls at the same time.
All right, then don't forget pen and paper to write down all the information that you gather.
Okay guys, so while you decide the best way to collect the data, I'm just going to pop into the lab, so you can find some more stuff to do experiment. Cool.
Right, to do the experiment, we'll need to record the results and put them in a table. Well, we'll need the mass of the balls and the time it takes the balls to reach the bottom.
That's a good idea.
Well, here we go. Look at this simple apparatus that we're going to use to release the balls exactly the same time from exactly the same height.
The balls are the same shape and size, but the blue ball has a mass of 300 grams, the red ball has a mass of 200 grams, and the yellow ball's mass is 100 grams.
I think we're all set. Okay. Will you record the times down there?
Sure, Aaron. Release the balls on 3. 1, 2, 3. Let's look at the experiment one more time. Clearly, this is a fair test. The balls are exactly the same in every way except their mass. The balls are released simultaneously and they all fall from the same height. Now notice again, they all hit the ground at exactly the same time. It took the balls 1,35 seconds to reach the bottom. That's exactly what Galileo found out when he did his famous experiment. He used cannonballs, we used stress balls, but the results would be the same with any other object of the same size and shape.
What will happen if the size and shape are different?
You know, that's a great question, Dineo. Let's find out. All right, guys, this is a pretty simple demonstration. I'm going to drop a coin and a piece of cloth from exactly the same height at the same time. See what happens.
But wait, isn't it obvious that the piece of cloth will fall slower because it is lighter?
That's a very common mistake that many people make, Lerato. Remember, we just proved in our previous experiment that it is not the mass of the object that causes them to fall slower than other objects. Have a closer look at the coin and cloth.
Okay, let's see.
Notice that the size and shape of these objects are very different. Could these differences cause the coin and the cloth to take different times to fall? The cloth has a much larger surface area than the coin. The differences between the coin and the cloth made people wonder what would happen if the same experiment was repeated somewhere where there's no air. That is why the coin and cloth experiment is famous. It was one of the very first experiments carried out by Neil Armstrong and Buzz Aldrin on the moon, but they used a coin and a feather. Also, remember that there is no atmosphere on the moon.
Now, we can't all go to the moon just to find out what happened during the experiment, eh? But there are ways to recreate those conditions here on Earth. Have a look. In this tube here, there's a piece of cloth and a coin. And this tube actually is a vacuum, which means it does not have any air in it. Now watch what happens when I flip the tube to cause the coin and the cloth to fall.
That's amazing, Aaron. But outside, the cloth fell slower than the coin. But inside the tube, the coin and the cloth reached the bottom of the tube at the same time. How is that possible?
Well, the air resists the motion of the falling objects. We call this air resistance. The coin cuts through the air more effectively than the cloth because of its size and shape. The coin has a lower air resistance than the cloth and so falls faster. When there is no resistance, for example, on the moon or in a vacuum on Earth, the time taken for objects to fall is not affected by differences in their size, shape, or mass. Now that we know that objects of the same size and shape, dropped from the same height, will take the same time to fall, what does this tell us about their motion?
Well, I think it means that the change in position or displacement of both the objects will be the same in the same time.
Right, Dineo. Remember that the change in position in a time interval is the velocity of the object. So we can say that the average velocity of these falling objects is the same. But is the velocity constant or is it changing?
Can't you answer that question by doing a ticker tape experiment?
Sure, Dineo. I've actually set up an experiment outside. Let's go find out.
Sure. First, we thread the tape through the ticker timer, then attach the mass piece to the tape. When the ticker timer is turned on, this little hammer strikes the carbon foil every 0,02 seconds. This makes a tiny mark on the tape, so the time between two adjacent dots is exactly 0,02 seconds. Now we allow the mass piece to fall, and as the mass piece falls, it pulls the tape through the timer.
The tape now gives us an accurate record of the mass piece's displacement and the time taken.
Correct. But you know what? Let's go back to the lab and analyze this information.
Sure.
Right. Now, to help us analyze this detailed information, I want you guys to please cut this tape into 0.1 second interval.
How many dots would represent 0.1s on the tape?
Remember that the time taken between two dots is 0.02 seconds. So we need 5 intervals, which are 6 dots.
After Dineo and Lerato cut the whole tape into 0.1 second time intervals, they measured displacement for each of the time intervals. Next, they pasted the segments next to each other to form a graph. Guys, Aaron, thank you very much for helping out with these experiments. I think it's time for us to go now. I'm going to take the data back to the studio where we're going to do some calculations and see if we can't find a way to describe the motion of falling objects a little bit more accurately. Let's go, guys.
Okay. Bye-bye, guys.
Bye.
Well, I really enjoyed our trip to the lab, and now we can analyze the data we collected together. Let's get started right away by having a closer look at this graph the learners put together. Notice, each of these segments of the tape represents the displacement of the mass piece in the time interval of 0.1 seconds. What do you think this tells us about displacement of the mass piece during each of the time intervals? Remember, displacement is the change in position. I'm sure you can see that the displacements for each of the time intervals are different. There is clearly an increase in each of the displacements for each of these 0.1 second time intervals. So we can say that the velocity of the falling mass piece increased during its fall. In other words, the mass piece is definitely not moving at constant or uniform velocity. But do you think that the velocity is increasing uniformly? I think we need to look at the measurements of displacement our learners made for each time interval. Notice the difference in the displacement between the second time interval and the first time interval is 0.096 meters, and the difference between the second and the third time interval is 0.096 meters. In fact, the displacement for each of the 0.1 second time intervals is increasing by 0.096 meters. Can you calculate the velocity of the mass piece for each time interval? Remember that the velocity of an object is defined as the rate of change of displacement. We find the velocity of an object by using the formula velocity equals change in displacement divided by time. I have filled in the values of velocity for the mass piece into this table. Look, the velocity increased by 0.96 meters per second for each of the time intervals. Can you see that the value of the velocity are increasing uniformly? Can you remember what we call any change in velocity? That's right, acceleration. Acceleration is defined as the rate of change of velocity. So, because the velocity of the mass piece is changing at a uniform rate, we can conclude that the mass piece has a uniform acceleration. But why do things accelerate uniformly when falling? Why in fact do they fall at all? Well, Sir Isaac Newton came up with an explanation. You may have heard of the story of him sitting under an apple tree and wondering why apples fall down. Could you explain why an apple doesn't fall up away from the earth? Let's investigate the theory Newton proposed. Sir Isaac Newton's answer to these questions was the idea of a force field called gravity. According to this theory, any objects that have mass and come close enough to each other experience a strong force of attraction towards each other. Well, the Earth has certainly got quite a bit of mass, and just about everything on Earth also has mass. So this force of attraction, or gravity, must exist between the Earth and all things on the Earth. Now, there are two factors that influence the strength of this force of attraction. A, the distance between the centers of the objects, and B, the mass of both the objects. Let me illustrate this concept of gravity a little further by using an example. When you hold a ball about 12 meters high above the surface of the Earth, you are resisting the gravitational force of attraction between the Earth and the ball. But when you release the ball, it's the gravitational force of attraction between the ball and the Earth that causes the ball to fall towards the Earth and to do so with uniform acceleration. We call this uniform acceleration the acceleration due to gravity, and we use the lowercase g to denote it. The acceleration due to gravity on Earth has a value of 9.81 meters per second squared downwards. This value has been calculated for objects falling in a vacuum. When objects fall in air, they have a slightly smaller acceleration because of air resistance. For our purposes, we will approximate this value to 10 meters per second squared downwards. On the moon, the acceleration due to gravity is 1,6 meters per second squared downwards. We use the symbol g with a subscript moon to identify this. Why do you think this value is so much lower on the moon than on the Earth? Think carefully about what affects the force of attraction between different objects. Now, here's today's task. A group of learners used a special multiple exposure photograph to collect data about the way this ball falls on Earth. The photograph shows the position of a ball at 0,1 second time intervals during its fall. Use this table of values to find the acceleration due to gravity. Remember, you can do calculations or draw a graph to answer this task, but you must be prepared to communicate your results and conclusions to others. Be sure to catch the next episode in this series on gravity and mechanical energy. See you then.